Alright, next lesson, we're looking at matter and energy. Basically, the stuff that makes up the world and then what we do with it. So, what is matter? The most basic fundamental definition of matter is anything that takes up space and has mass. So, look around the room that you're in right now. What in the room that you're in has mass and takes up space? You do. Your computer, phone, or tablet that you're watching this on does. So does the chair, the table, possibly a TV, whatever else is in the room that has mass and takes up space, that is matter. So, which also begs the second question. What in the room doesn't have mass or take up space? So look around the room and try to think about things in the room that don't have mass and don't take up space. Air is not an answer because air does take up space. It fills the room. We know it takes up space because if you blow up a balloon, it all of a sudden has volume. The air that's in the balloon takes up space. We also know it has mass. If you weigh an empty balloon and then you blow it up and weigh it again, it will weigh more. All right. So things in the room that don't have mass and don't take up space are things like light, heat, and sound. Now, sound requires matter in order to move. There's no sound in a vacuum. But sound itself does not have mass and does not take up space. All right, so now we need to be able to describe matter. So that's what matter is, anything that takes up space and has mass. So now we need to be able to describe it. And we describe matter in terms of its properties and its changes. And there's two types. We have physical properties and changes. Now, the key thing about a physical property or change is that we're describing the object and we're changing the object, but its identity remains unchanged. So this leaf, I can measure it. I can tell you its color, that it's brown. We can weigh it. We can measure its length. We can measure the length of the stem, measure the length of all the veins. We could draw a picture of it and show where all the holes are that are in the leaf. Those would all be physical properties. A physical change would be something that we do to the leaf that still leaves it as a leaf. I can tear it. I could crumple it. I could paint it, spray paint it orange. Well, even though I changed its color, it's still a leaf. Its identity has not changed. This is in contrast to what we call chemical properties and changes, because chemical properties and changes change the identity of what I'm dealing with. If I take that leaf and I light it on fire, it is no longer a leaf. It is now ash and gases in the atmosphere. So one of its chemical properties is that it is flammable. Okay? Same thing with the wood in this picture. It is flammable. When that fire is done, that wood is no longer wood. It has now changed into something else. Ash and gases in the atmosphere. Another good example, rust. Rust is a chemical change. Okay? And the fact that iron can rust is a chemical property. Because rust is iron oxide, and that's different than iron. Its identity has changed. Another everyday one that you're going to run into is baking. When I take sugar, flour, eggs, and milk, and I mix them together to make pancakes on a Sunday morning, a pancake doesn't taste like flour and eggs. It has changed into something else. The cooking process has chemically changed it. And so that's a good example of what's going on there. So we can also describe matter by breaking it into categories. So when we look at matter, we can describe it into two categories, what we call a pure substance or a mixture. Now, a pure substance means I have one thing and one thing only, and then a mixture would be two or more things mixed together. So pure substances can then be divided into elements and compounds. So an element is the simplest form of matter, that you have just something that's on the periodic table. You have a tank full of just oxygen gas. You have a handful of carbon. You have a pool of mercury. Okay, it's just one element and that's it. One thing from the periodic table, that's it. where a compound is going to be some chemical combination of elements in what we call a fixed ratio. And so like water, H2O, 2 hydrogens for every 1 oxygen. Glucose, C6H12O6, 6 carbons, 12 hydrogens, 6 oxygens, chemically bonded together. Okay. So those are your pure substances. You can have a pure pile of sugar. You can have a pure bottle of water. Okay. Now, mixtures come in 2 flavors as well, what we call homogeneous and what we call heterogeneous. So just looking at the prefixes, homo and hetero. Homo means same, hetero means different. So a homogeneous mixture is uniform throughout the entire mixture. So a good example here is a can of Coke. Coke spends a lot of money making sure that every sip you take tastes the same. So if you took a sample from the top of that can, the middle of the can, and the bottom of the can, they would all be identical. Okay, they're uniform. Same thing if you took samples of air in the room that you're in. They would all have the same amount of humidity, the same amount of pollutants, the same amount of pollen, same amount of dust, would generally be the same throughout the room. Heterogeneous, on the other hand, are things which are not uniform. A classic example here is if I go to Dairy Queen and I get a Snickers Blizzard. All right, that I can have 1 spoonful that's like all Snickers and very little ice cream. Then I can have another spoonful that's half and half. And then finally I can take my last spoonful out of the bottom and it's going to be like just ice cream and no Snickers at all. Every bite's different. It's not uniform. A salad is another good example of a heterogeneous mixture. So for those of you who like straight up definitions, here are some for you. An element is a substance that cannot be separated into simpler substances. You can't take a carbon atom and make it any smaller and still have elements. Once you break a carbon atom up, you're into subatomic particles and it just gets different. All right, compound is a substance made of fixed ratio of elements, and I would add to that just chemically connected or chemically bonded together. Because that's what separates a compound from a mixture. That, just like we talked about chemical properties and chemical change versus physical property, physical change, that, when I have water, if I try to separate out the hydrogen from the oxygen and I separate them, I no longer have water. Its identity's been changed. I now have hydrogen, a flammable gas, and oxygen, a gas that's required for combustion, neither of which are liquids that put out fire. Okay? A mixture is different. A mixture is a physical blend. When I have a salad and I don't like the cucumbers, I can take the cucumbers out and they're still cucumbers. The lettuce is still lettuce. I could let the ice cream melt in my Blizzard and I could strain it out and I could get the Snickers left behind and I could have the ice cream in the bottom, of the colander, that kind of thing. And then the 2 mixture names. So with mixtures, like I said, they're physical combinations, so they can be separated by physical change without changing their identity. And so that's our next section here. So for example, coffee. Now, a good cup of coffee is a godsend, but a good cup of coffee should not have coffee grounds in it. And so I'm going to filter it. So I'm going to filter out the coffee grounds so they stay in the filter and the coffee goes to the bottom. Distillation. So distillation, in this case, is how we make our stronger spirits. Because if you take a mixture of water and alcohol and you boil it, the alcohol is going to come off first because it boils faster. It boils at a lower temperature. And so the alcohol comes off and then you collect it and then you get a stronger version of alcohol. This is also how we get things like kerosene, gasoline, diesel fuel, and motor oil all out of 1 barrel of crude oil. Is that all of them evaporate at different points. And so they use what's called a distillation column, and they can separate a barrel of crude oil into different components: kerosene, gas, diesel fuel, motor oil, and the such. All right, crystallization. Here's a picture of the salt flats. If you take a mixture of salt and water and you evaporate off the water, you crystallize the salt that's left behind. It's how they make rock candy. Same idea. And then chromatography is one probably not as familiar to you. But if you take like a marker, a marker seems to be, almost like the color seems uniform. It seems to be the solid thing. Doesn't seem to be a mixture. But if you do it on a thin piece of paper or like a coffee filter, it's a cheap, easy way to do this one, and then put some water or rubbing alcohol on the edge, it'll cause the dye to move and separate into its components, showing you that it is indeed a mixture. So that's matter. We in chemistry are going to spend most of our time talking about matter and less of our time talking about energy. Because at its core, energy is the capacity to do work or to produce heat. And in chemistry, we're more concerned about the heat part. The capacity to do work, that's more physics. And so physics is a lot about energy. And we're less about energy in chemistry. But within chemistry, we have three major types of heat, or energy. Sorry, not heat, energy. We have radiant energy. Think of the sun, a fire, a heat lamp. Those give off energy that we oftentimes feel as heat. It radiates off. We have kinetic energy. This person jumping off a cliff. And they have kinetic energy, the energy of motion. Okay, they're going to go faster and faster until they hit the surface of the water. That same person also, before they jumped off, and even now, middle of the air, they have potential energy, stored energy, caused by the height and gravity. When it comes to chemistry, you wouldn't think this just from what you probably know now, but the most important of these three is going to be kinetic. The energy of motion plays a major role in how things behave chemically. And we'll see that when we get to states of matter later on. Within chemistry, we have two units of heat. We have the calorie, which is kind of what you're familiar with in terms of food. Even though that's a dietary calorie, it's a little bit different. And then we have the joule. The joule is the SI unit of heat, and that's the primary one we will use in this course. And then we also have, it's important to know that we have the law of the conservation of energy. That energy is neither created nor destroyed. It simply changes forms. The only possible exception to this, and it's not even really an exception, is just that in a nuclear reaction, energy and matter are interchangeable and they go back and forth. Once again, they're not destroyed or created. They simply change from one to the other. And so there we are at the end of this lesson. Look forward to seeing you in the next one.